So in the case of dissolved oxygen, what it is, this may not work. Okay, it's all right, I got a plan. What dissolved oxygen measures is the amount of oxygen gas that's trapped in water. And if you think about water as being like little pieces of something, some of you probably know, you might remember from work that we've done or other classes, that water molecules are made up of one oxygen atom that are attached to two hydrogen atoms. Kind of looks like this. Oxygen gas has one oxygen atom attached to another oxygen atom. And I think it might be I can't remember, it might be 3 or 2, it doesn't matter. The chemistry isn't important. But we can think of these things as little pieces of stuff. And neither one of them is particularly big. And so if we were to take a glass of water and look at what's inside that glass of water, what we'd see is there would be some pieces of water. Mostly what's in there is water. But in addition to all the water that's in there, we would find there are little tiny trapped chunks of oxygen gas, just mixed in. And they are potentially able to move out of the water, and some of them do, but some of the oxygen gas in the air moves into the water. So there's this like movement back and forth through the surface of the water. And this oxygen gas is a little bit stuck in there. It's not stuck, but it's a little bit stuck. And what causes it to stick is that these molecules can kind of stick to each other. These pieces right here, these oxygen atoms, stick a little bit to these hydrogen atoms. Sometimes that's called a hydrogen bond, so you can get these little hydrogen bonds showing up. The other thing is that they're kind of physically trapped. So imagine if I was an oxygen molecule and you all were water molecules, and I wanted to get from the middle of a bunch of water molecules to the exit. In order to get there, I have to get through you. And there is an actual physical blocking. If I were to walk straight from here to the door, I would have to get through everybody. And it's not just a straight path to the door. So these oxygen molecules are trapped inside water. And there's oxygen in virtually every water source that we can find. It's almost impossible to find water that has no oxygen in it at all, because it comes in from the air. We measure dissolved oxygen, and I'll show you this in just a couple minutes, but we measure it. There's a couple different ways we can look at it. One, we can look at it in units of parts per million, or we can look at it in units of milligrams per liter. And the sensors that we're using measure in milligrams per liter. But we do use optical sensors. That's what we have. We only have one, and it's like $400. So when we measure dissolved oxygen, I'm going to do it because it also it works best if you make the measurement at the actual location where we want to know. So we'll take our dissolved oxygen sensor outside, make our measurements with it outside, and I'll be the one to do that because we just have one. I don't want it to break, or if it does break, I don't want it to be any of you that breaks. I'd rather have me be the one that breaks the equipment. There's other ways to do it as well. We didn't used to even have sensors to measure dissolved oxygen. It used to be a chemical test. There are things that will react with oxygen. So people would go and they would collect water in these special vials that prevented the oxygen from leaving. And then we would put it into test tubes, and we'd add chemicals and things would change color, and we would literally look at, it was like those pH tests. We look at the color of something and use the color to determine how much oxygen was in there. And then the reason that dissolved oxygen is important is pretty straightforward. It doesn't matter for a whole bunch of things that we use water for. The dissolved oxygen in water doesn't affect whether or not we can swim in it or boat in it. doesn't have any effect on whether we use it for like watering crops. It makes no difference to us when we drink it, or bathe in it, or cook with it. The only thing that dissolved oxygen does is it is beneficial for organisms that live in the water. And the reason for that is because anything that lives in the water still needs oxygen. So if you think about fish, or the little bugs that are living in and under the water, they need oxygen in order to survive. They're not coming up to the surface and breathing the air. They get their oxygen from the oxygen that's dissolved in water. And it's really important. Primarily for fish and the organisms that fish eat, all of which live in constantly submerged water. They don't breathe air. They can't breathe air. And so we care a lot about dissolved oxygen. And we measure it, we look at it in lakes and streams and creeks, we even look at it in the ocean. Some of you may have heard of something called a dead zone. Raise your hand if you've ever heard that term before with reference to the ocean. Dead zones are places where a combination of events have occurred that have basically sucked tons of dissolved oxygen out of the water. And we will talk about how this happens. I'm not going to talk about it today, but basically what happens is that if you grow a bunch of like aquatic plants and then they die and then they're eaten by bacteria, the bacteria use up a ton of oxygen. So typically what leads to these dead zones is fertilizer. If you like add accidentally, you get a bunch of fertilizer into the ocean, then a whole bunch of aquatic plants grow, and then they die, and then the bacteria feed, and then there's no oxygen. I mean, there's some, but not enough to sustain wildlife. So these dead zones are really important, and where we tend to see them is places where there's rivers that are flowing out to the ocean that are polluted with fertilizers. So lots of dead zones in the Gulf of Mexico, for example, because the Mississippi River carries tons of fertilizers from every state that has farming, which is all of them. All the fertilizer that comes off those crops ends up in the Mississippi River, and then it all comes down and it goes into the Gulf of Mexico, and almost every year there's a big die-off because of the lack of dissolved oxygen. But we'll look at that more later. So at this point, what we've talked about is dissolved oxygen. We've talked about turbidity, conductivity, pH, and temperature. Those are the 5 water quality parameters that we're going to look at. And in just a minute, I'm going to talk to you about a couple ways that we can think about with respect to our creek. A couple of ways that we might think about that those might be important. But before we do that, I just wanted to show you our dissolved oxygen sensor. So I have it set up already, and what I did is I put it in a what's called a calibration solution. This calibration solution is designed to have almost no dissolved oxygen in it. So right now it's measuring 0.05 milligrams per liter, which is a really small amount of dissolved oxygen. And then what I'm going to do is put the cap on this before I spill it. I'm going to take this and rinse it off. Okay, and then pop it in to some just tap water. And when I poured this tap water in, it splashed and a bunch of air came in. So this tap water is probably higher in dissolved oxygen than it was when it was in the faucet. But you can see it was 0.05. Look at how quickly it's going up. My guess is this will be this will end up maybe somewhere around 8 or so. That's my guess, is that it'll be somewhere around 8. We talked before about the idea that as temperature rises, dissolved oxygen goes down. You may not remember that, but I talked about that last week. And so one of the things that we should see over the course of the class period today is, as this sits in this container, once it kind of stabilizes, the dissolved oxygen should start to drop, because this water is relatively cold right now, and it'll warm up. And as it warms up, the dissolved oxygen will decrease. The other thing that's going to happen is the oxygen that was put in there right as it was coming out of the faucet, because it was mixing with the air, there was lots of turbulence, that is probably going to come out as well. So what we'll see is this is going to end up, so it's looking like, you know, I don't know exactly where it's going to end up. I guessed 8. So it looks like it probably will come, you know, somewhere between 7 and 8. And we'll just take a look, and then once it stabilizes, then we'll watch it and we'll see what happens over time. So at this point, we have the capability of measuring any one of a number of different water quality parameters. We can measure dissolved oxygen, pH, conductivity, temperature, turbidity. All of those things, as we've talked about, can affect a wide variety of potential things that people might care about. The quality of water for drinking, the quality of water for wildlife, whether it's useful for cleaning things, whether it's useful for watering crops, or running through industrial parks and factories to cool things off. And what I want to do next is have you think about a couple of different pieces. One piece is the physical conditions of the water. So if we were to go outside, for example, and look at the creek, you'll be able to, without making any measurements of water quality, there's things that you'll be able to notice. You'll notice places where the water is more shallow or more deep. You'll notice places where there's more shade or less shade. You'll notice places where it seems to be moving faster or slower. You may notice places where there's more rocks or more like kind of mud underneath the soil. All of those things could potentially have an impact on our water quality parameters. And so one of the things that we're going to be thinking about is how do the things that we see about the creek relate to the things that we can measure about the creek? And you'll work on that a little bit today. Starting next week, we're going to add one last thing to look at, and it's the most fun, and that is something that allows us to look at the organisms that are living in the water. And for the most part, there are a bunch of things that we're just not going to be able to measure. We're not going to be able to catch fish. Some of you will probably have the opportunity to look at some crawdads, but it's really hard to get out there and catch trout and salmon and stuff. There's not that many in the creek, and it's really hard to catch them anyway. But there is something that we can capture. And you do not have to write any of this down. We'll go through this again next week, but I want it to be in the back of your mind before you start doing the work that I'm going to ask you to do today. And those are aquatic macroinvertebrates. And aquatic macroinvertebrates are tiny critters, but you can see them they're easier to identify under a microscope. But in general, we can see them with that, they're not microscopic, they're macroscopic. And they're invertebrates. They don't have backbones. They don't have bones at all. And like I said, you don't have to write any of this stuff down. But a lot of times, they're larvae for things that fly around. So mayflies, for example, we've all seen mayflies. You might not know it, but there's mayflies all over the place. But they spend a significant amount of time in the water, looking like this, these little kind of creepy crawly things. They're really neat. So there's 3 pieces that we're going to put together here at the same time. The first piece is the measurements we can make about water quality: temperature, pH, conductivity, turbidity, and dissolved oxygen. The second piece is physical observations that we can make about the water. Measurements, maybe. how deep it is, how fast it's moving, whether there's lots of shade, whether there's rocks or mud, or there's all sorts of stuff that we can visually observe in the creek. And then the third piece is these organisms that are living in the water. And we're going to ultimately use these to kind of help verify the conclusions that we draw when we collect some data. So what we're going to be doing over the next couple of weeks is making measurements of water quality parameters. We'll do it pretty much every day, starting on Tuesday, not Monday. We've got something else going on Monday, but starting Tuesday, we're going to make some water quality parameter measurements so that we have just a rough idea of how different spots in the creek compare. And then we're also going to construct these little, I call them brick packs. We're going to take a brick, and we're going to tie a bunch of leaves to them, and we're going to put them in the water, and we're going to leave them there. And these aquatic macroinvertebrates will crawl into them because it's great habitat for them. And then we will pull the bricks out of the water next week on Thursday, and we'll examine the organisms and count and see if we can figure out some stuff about what's in the water. We'll look at which organisms are there, and we'll do a calculation of their diversity, kind of the same way that we did a calculation of diversity for soil organisms, only you're going to do a little bit more of the work. All right, so this is a third piece that we're going to add. I'm not going to talk about this anymore today, but I will go through this on Tuesday. We'll get stuff set up. Okay, so I'm going to pause there for a second and ask if anybody has any questions about either dissolved oxygen or about aquatic macroinvertebrates, just that brief overview. Okay, this is, by the way, look, it was up, remember it was up all the way to like 7? It's dropping now. While I talk over the next minute, oh look, there, it just dropped down. So this is what's happening. The dissolved oxygen that's in there is actually coming out. We could replenish it by kind of splashing it around. And I will in a couple minutes. I'll take this and I'll kind of shake it a little bit carefully. It'll probably spill a little bit, but try not to damage the sensor. And when I shake it around, you'll see the dissolved oxygen will go back up again. So we have a way of looking at water and determining whether or not it might be high or low in dissolved oxygen. Water that's splashing probably has more dissolved oxygen. So we'll come back to that in just a minute. What I'm going to ask you to do today, I'll give you a quick break first, but then what I'm going to ask you to do is in your work groups, I'm going to ask you to start doing some research into the study that you're going to carry out over the next couple of weeks. So this is called the water quality study, and what you're going to do is evaluate some of the parameters of water quality that we talked about: pH, conductivity, turbidity, temperature, dissolved oxygen, some combination of those even. You can look at more than one if you want. And you're going to try to investigate whether there's any connection between those water quality parameters and some of the things that you can see and observe in the creek. There's a whole variety of things that you could potentially look at. So what I want you to do today, we'll take a break, and then when you're back from your break, you'll start on this. What I want you to do for today is, in your work groups, I want you to go through all 5 of these steps. And I'll help you, and I'll kind of coach you about when you should be done with each of the steps, so that you all get finished with this in your groups by the end of the class period. I want you to type your work individually. So if you're working with your work group, you're going to all be talking about stuff, but you're not going to have one shared document. You're all going to be typing what you're hearing and what you're thinking separately. Okay? So this is going to form the basis of the water quality study that we're going to start next week. We'll do our data collection over a 2-week period and wrap it up with an analysis and a report on the Thursday before winter break starts. All All right, does anybody have any questions before we go on break and then start working on this? Okay, it's 12:35, come back at